Yeah, dear students, welcome to the Visual Analytics lecture. We want to discuss today dimension reduction. I think that is quite an important topic. A lot of research activity has been carried out in this area. Dimension reduction is part of many visual analytics pipelines, so therefore I want to start here also with a pipeline. Often dimension reduction is one of the earlier steps. It may involve even some pre-processing before. And then the results are used for visualization, for interactive visualization and analysis. And the analyst may go back and to restart dimension reduction again with different parameters, for example, or by choosing another algorithm that leads to different visualizations and different analysis results as well. Yeah, so dimension reduction I think is quite important. I prepared two slide sets for dimension reduction. This one is the shorter one. The next one is larger, so I expect that we will have 3 video lectures on dimension reduction. This is the first. And today I want to describe feature selection, criteria for dimension reduction techniques, and I will discuss a bit more a few linear projection techniques like principal component analysis, PCA, and factor analysis. There are many more, like independent component analysis or linear discriminant analysis. I just want to briefly mention them, but for the sake of time, I cannot explain them in detail. In the next video lecture, so that will be not be part of this one, I will discuss nonlinear techniques. Yeah, projection pursuit is one of them, multidimensional scaling, and t-SNE, stochastic neighborhood embedding based on a t-student distribution. And the whole lecture should not only discuss techniques that can be applied to the data and then more or less automatically create a result. We also want to discuss how the analyst can assess the quality of the resulting projections. If we have many dimensions and reduce them, that means we project it to a lower dimensional space that necessarily involves a projection error, a certain loss of information. And this loss of information is not everywhere the same. Yeah, there may be some parts of the projection that are quite faithful, where distances in the high dimensional space are preserved quite well, whereas in others this is not the case and we make stronger errors, and that should be obvious to the analyst. How strong is the error? What is the local and global quality of such projections? And of course, it's particularly convincing if the user then has possibilities in order to adapt the dimension reduction and with this to improve the error with respect to certain regions or certain properties of the projection where she is particularly interested in. And yeah, finally, we want to discuss a process for dimension reduction that is guided. That means some visual aids are provided that make it easier for the user to predict what will happen if I use this or that dimension reduction technique with this or that parameter set. Yeah, so that's the final part of this, and I think then we have a round picture of dimension reduction. Yeah, let me start and motivate this a bit. In visual analytics, we typically think about the analysis of data that has more than 2 or 3 dimensions that could be directly shown on a computer. We have higher dimensional data. And higher dimensional data is both hard to analyze and hard to visualize. Yeah? Traditional knowledge discovery techniques such as clustering, decision trees may get very slow if we have many dimensions and many data sets. Yeah? And the same is true for the visualization. So dimension reduction basically aims at finding a lower dimensional representation of the data where the major properties are preserved quite well. What are the major properties? The major properties include clusters, yeah, something that was close to each other in high dimensional space should, after dimension reduction, be again close in the projection space. Also, outliers should still be recognizable. These are examples for features that should be preserved. Yeah? Dimension reduction involves algorithms that do one of two things. One is to remove irrelevant dimensions, and that is called feature selection. And the second one, and that is the core of dimension reduction, is to transform data in another space where less dimensions represent the data. That does not mean that we really remove data from our original set of dimensions, but instead we come up, for example, with linear combinations of the original dimensions, and we need fewer of these linear combinations than the original dimensions. Yeah? You see here already that we have this confusion between the terms dimension and feature. That's basically the same. Yeah? But algorithms that remove irrelevant dimensions are developed in machine learning, and they are referred there as feature selection. So features are dimensions. Yeah? But we never speak about feature reduction techniques. There the typical name is dimension reduction. So we have to bear a certain amount of inconsistent use of these two terms. I mentioned already that dimension reduction, I often use this abbreviation DR, as you see here, involves a loss of information. And I also started to comment a bit on important structures that need to be preserved. I mentioned clusters and outliers already. Correlations are also important. Yeah, if I see that the data is correlated in a certain way in the high dimensional space, it would be desirable that this can be perceived in the projection as well. And manifolds is another property. So imagine that we have two-dimensional data that is arranged in such a way that the data are on a circle, yeah, on a linear structure, on a one-dimensional structure. That is something we would like to recognize, even after the projection. The origins for dimension reduction are in psychology, and some techniques have been specifically developed in psychology. In psychology, researchers or also routine psychologists use a number of questionnaires with many questions to understand the state of a patient and finally to come up with a diagnosis, or after some treatment they want to understand whether the treatment was successful or not. And there the goal was not only to have these many questions and answers of the patients, but a little bit of a high-level summary that provides the most important personality traits based on the many individual measurements. So that's the origin in psychology. Dimension reduction now is used in statistics, in machine learning, and in visualization or visual analytics. Slightly different techniques are used. A few years before, I could supervise a master thesis of a mathematics student. So he worked in statistics and he dealt with dimension reduction, and I really had to learn a lot because in statistics they really use different algorithms for dimension reduction, and they also have a slightly different perspective on dimension reduction. The appropriate techniques strongly depend on the data, in particular on the number of dimensions, but also on the distributions of the individual dimensions. And appropriate techniques also depend on the tasks. That means what are the things that the analyst wants to see and wants to analyze with these data. Yeah? So therefore one may really say that the selection of an appropriate dimension reduction technique combined with certain parameters that may be necessary and the exploration of the results is quite challenging. Often something that a domain scientist as an end user cannot sufficiently and efficiently do herself. Imagine a 10-dimensional dataset. If we would like to show this data completely, we could use a scatter plot matrix, as we have discussed in one of the earlier lectures. That would lead to 45 scatter plots that are unique and that have to be analyzed. Yeah. What easily may happen is that there are clusters in these 10-dimensional data that are not recognizable in any of these 45 scatter plots. Yeah, that's a bit unfortunate. Dimension reduction techniques here would search for hyperplanes or curved planes to reveal structures such as clusters. So dimension reduction aims at a generation of a lower dimensional, that's abbreviated here with LD, a lower dimensional visual representation that is similar with respect to the high dimensional data. That means only elements or data sets that are close to each other in the original space should be close to each other after projection. Yeah. A dimension reduction technique is often used to provide an overview of the data. There is nothing bad of having a scatter plot matrix with 45 scatter plots, but it would be nice to have in addition an overview that may guide the user a little bit in the analysis of other visualizations and more detailed visualizations. Yeah. So dimension reduction also helps to support the user in navigating the data and browsing the data. That is a further important use case. Dimension reduction builds on an objective function that measures the discrepancy between the similarity in high dimensional space and the distances. It benefits, as we will see, from a tight coupling of algorithmic components and visualizations. So I try often to find links and connections between the individual topics of this visual analytics lecture in order to find something that makes it easier for you to correlate things and also to remember them. So here I try to find a relation between dimension reduction and subspace clustering. In subspace clustering, we first search for clusterable subspaces, right? That means for subspaces where we have strong differences in the local density of the data. Not every dimension belongs to any interesting subspace. Yeah? There are certainly dimensions in a higher dimensional data set that do not belong to any interesting subspace. If this is the case, probably this dimension is also not very interesting from a dimension reduction point of view. On the other hand, if a dimension contributes to clusters and users look at these clusters and are confident that this cluster really is semantically meaningful and essential, then such a dimension probably should be preserved. Yeah? So that is the dimension, the relation between subspace clustering and the question whether or not dimensions are relevant or not. That is particularly important for the feature selection step. Our data has a certain dimensionality, yeah, based on the questionnaires that we have provided or the observations and measurements that we did. Yeah, a certain dimensionality, maybe quite large, but it may have a lower intrinsic dimensionality that captures most of the variance, can explain most of the data. So dimension reduction is often about finding this intrinsic dimensionality. Yeah. And then we have to find, of course, an appropriate visualization. Let's assume that our dimensionality was originally 18 and we find out that the intrinsic dimensionality is 7. Yeah, then we need something to show 7-dimensional data, for example, parallel coordinates. Yeah. One topic that is also related to dimension reduction, therefore I want to mention it here, is the development of scores. That is something that is not done automatically, at least typically not, that involves a lot of experience. Scores summarize a number of information in one value. And then we have some thresholds for this value that help us to come up with certain decisions. It's really something that supports decisions. Yeah? So such scores are used, for example, in credit score assessment. Yeah? If you want to go to a bank and you want to have a certain credit, maybe not too low, then the bank will collect a number of information from you in order to assess should we give this person such a credit or not? Yeah, one of these information would be, of course, your age. You are quite young, that's good. Yeah, so you have plenty of time to pay the credit back. Yeah, a person with the same conditions like you have that is 70 years old, well, that would be not so nice. Yeah. In medicine, there are also scores that help to decide on treatment that are used in order to characterize the risk that is involved with a particular disease. So in general, these scores are weighted combinations of several values. And yeah, this weighting needs to be carefully adjusted, of course. If we reduce the information from a five-dimensional space, for example, to a one-dimensional score, then of course we have an information loss. Yeah, as I mentioned this already, that is only an approximation. But often, for example, for the sake of time, we need such approximations. Yeah, so scores are designed to minimize such errors. Let me give you two examples, or briefly mention them at least. The Framingham score was the result of a large health survey related to cardiovascular diseases, yeah, like coronary artery disease or heart infarction. So the risk for a cardiovascular event was assessed based on age, blood pressure, whether or not the participants smoke and how strong they smoke, if so, and the cholesterol level. There are two values, the total cholesterol and the HDL. There's also LDL that has not an influence here, but HDL has an influence. What is a cardiovascular event? Event in medicine is nothing nice. Yeah, you may think that an event is a nice thing connected to a party. No, here an event is, for example, a heart infarct, something severe that happened, and the risk for this should be determined. And the Framingham score is a summary of these different values within one value. The Child-Pugh score is a score that is developed for persons with chronic liver diseases, and this is particularly persons with cirrhosis. And it is based on 5 measures. Yeah, I briefly show them here. These are the 5 measures: bilirubin, albumin, prothrombin, ascites, and hepatic encephalopathy. All of these are measurements, or at least these are measurements that are taken from blood samples. Yeah, and there are some thresholds defined. If the values are quite low, here for this example, you get 1 point, or if it is quite high for this value, you also get 1 point, and you get 2 points for moderate values and 3 points, yeah, if you have high values for bilirubin or very low values for albumin. So that is designed in such a way that 1 always means low risk and 3 means high risk. Yeah. So if you have these 5 points, you can sum them up, which means you have at least 5 points, and the maximum would be 15. And the Child-Pugh score, that's a rough coarse classification of the patients, discriminates 3 classes. Class A with 5 to 6 points. That means almost always we have the minimum risk variant. At most, in one criterion, we can have a moderate risk. Then we end up in class A, and here is the 1-year survival and the 2-year survival for persons in this class A group. If you have moderate values, we are in the class B group, and if we have a high risk, that means at least for one of these criteria we have a high risk, maybe even for more, then the survival is considerably lower already after 1 year. Yeah, so that's the message here of this Child-Pugh score. So let me describe feature selection that is often used in machine learning as a first step, and it could be also used in visual analytics as a first step. Maybe we have 50 dimensions, and with feature selection we reduce these 50 dimensions to 23, and then we can come up with dimension reduction, which provides a 2-dimensional projection or a 3-dimensional projection that we can show on the screen. I only briefly describe one feature selection method because feature selection is more of a topic in machine learning and data mining and less of a topic in visual analytics. Yeah. So here is one quite famous algorithm, correlation-based feature selection. The basic idea here is that we add features only if the feature that we add is not strongly correlated to the features that we already have. Yeah, that is a quite reasonable strategy because it basically means that the feature that is added cannot be easily predicted from the features that we already have. Yeah, it is somehow independent and orthogonal to the features that we have. The algorithm starts with an empty set of features, so at the beginning we have nothing. And then we select a first feature, maybe it's a random choice, that provides a high information gain. So we could, for example, compute the entropy for all the data, probably after some normalization. And then we sort the features according to entropy and we choose the one that has the highest entropy. That's our first feature. We add it to our set. And then we look for further features that again have at least not a too low entropy and that are not strongly correlated to any of the features that we have. And this line of thinking leads to the computation of a certain merit value. Yeah? So for any candidate feature that we may add to our set, we compute this merit value, and as soon as the merit value starts to decrease, yeah, it is constructed in this way that it can also decrease, then we stop adding further features, then probably it does not get any better. Yeah? This merit value is basically indirectly proportional to the feature dependency, and that is basically the correlation coefficient. Yeah? Tommy Hielscher in this paper that is in the list of references after the next slide set discusses this problem a bit more, how this is related. Yeah, so that's the basic algorithm here. I think that's not too difficult. Yeah, so from now on I want to describe dimension reduction, and dimension reduction differs from feature selection, to make this clear again, in the sense that no dimensions are removed, but all of them are taken together, weighted somehow and projected to a lower dimensional space. And if we have a linear dimension reduction techniques, that means that the dimensions that we have in our projection space can be computed as linear combinations of the original dimensions. Yeah? Linear techniques are suitable if we assume that our data in all dimensions is normally distributed. That means it follows this Gaussian curve that you know. It must not be strictly following a normal distribution. It may slightly deviate from this, but if we have data that is highly asymmetric, for example, then the expressiveness of a linear projection technique is really reduced. Yeah? So in particular for skewed or multimodal distributions where we have different peaks in the data, not just one like with a normal distribution, this would be a situation where nonlinear techniques are better. So, and advanced techniques also incorporate some a priori knowledge. Yeah, so it's even possible, we will see an example for this as well, that we apply dimension reduction not to the full set of the data, but instead to individual clusters. Yeah, and then we will have different results for the individual clusters. Yeah, sometimes it may be useful not to treat the whole data set as something uniform and homogeneous, which it often is not. Major dimension reduction techniques are available in R, in MATLAB, and in other libraries as well. Yeah? This includes at least principal component analysis, multidimensional scaling, and T-stochastic neighborhood embedding. Yeah? These are the three most frequently used techniques, and therefore they have been integrated in the libraries. or maybe they were integrated in the libraries and later they were used so often. I'm not quite sure what was first, but definitely that is the case. These techniques are widely available. I will briefly discuss that the results also depend on some pre-processing. T-SNE, as we will see in the next video lecture, is even a stochastic technique. So that means even if it is applied to the same data with the same parameters, it does not end up in the same result. Yeah, there is a random component included. Yeah, pre-processing. First, in the dimension space, we can remove dimensions with low variance. That could be achieved by a sorted histogram that shows the variance for all dimensions. Yeah, and if we detect that some dimensions have really a rather low variance compared to the other dimensions, that could be a sign to remove them. Yeah, that could be done interactively or in the way of a feature selection algorithm. So, and the second thing that could be done is, in case that we have strongly correlating dimensions, we can average them. Yeah. So, for example, in health surveys, often it is registered what is the hip circumference, what is the waist circumference, and what is the body mass index. These three features are highly correlated. So one could generate one feature based on these three, like a score, that could replace the other two. Yeah. An important aspect here is we need to normalize the data when we want to do this. The ranges may be very different, and even in the example that I just presented, body mass index and waist circumference have different measurement units and also different ranges that needs to be normalized first. As a visual aid, one could imagine a color-coded correlation matrix, which basically says that objects that are highly correlated get a certain color, yeah, typically a strongly saturated color, which emphasizes these pairs of dimensions that are strongly correlated. And then the analyst can decide, yeah, perhaps to replace one of them or remove one of them, or to replace both with a kind of average. Yeah, so that would be a pre-processing in dimension space. Pre-processing is also useful in the item space, and here in particular it is useful to search for outliers and consider to remove them. Yeah? Dimension reduction algorithms like principal component analysis often are quite sensitive to outliers. And if an outlier is based on unreliable information, of wrong information, a broken sensor, for example, then this really should be removed. Yeah, this is from the DIMSTiller program from Ingram and Tamara Mansner, and this shows, this is part of a guided process. I will explain this guided process later in more detail, but here we see these visual aids in pre-processing. Yeah? The matrix that indicates via color the correlation values, and red and blue means high positive or high negative correlation, whereas this low saturated yellow would represent a very low correlation. So here we see the variance for the individual dimensions, and we see here are some of the dimensions that really have a low variance. Maybe we can get rid of them. By the way, the first 29 dimensions have an almost not measurable variance. So basically their most values are the same, and then they are not interesting, of course. This is a very simple point set and illustrates the idea of dimension reduction. So we could think about how to project this two-dimensional space to 1D, or how to reconstruct the points in this three-dimensional space to 2D. So if we want to reduce the two-dimensional set to 1D, then basically we have to compute a line, a regression line that fits the data, and the projection error is basically the orthogonal distance here from these points to the line that we have fitted to the data. And as you remember from our discussions of correlation coefficients, if this one point here would be far away as an outlier, the line would look much different. Yeah? So here we expect that a plane is fitted to the data could look like this. Yeah? Reduction of these three-dimensional data to 2D. Yeah, then the linear techniques that I want to explain a bit are principal component analysis, widely used, and factor analysis, not so widely used in visual analytics, but in psychology it's quite frequently used. Yeah, let me start with the principal component analysis, often abbreviated with PCA. This technique was introduced, I think, with a different name, but it was introduced in 1933 already by Hotelling. Yeah, I think it was initially called Hotelling transform. So we have our original dimensions in the data, x1, x2, xi to xp, and the principal component analysis does not remove any of these dimensions, but it generates a new coordinate systems, again with orthogonal dimensions, and the new dimensions are linear combinations of the original dimensions. That means a weighted combination of the original dimensions. And the principal components are sorted according to variance in these new directions and dimensions. Yeah? Each principal component carries a loading, and that loading tells you how much of the variance of the data is explained by this principal component. Yeah? Maybe we have 10-dimensional data, and maybe the cumulative loadings of the four principal components is 0.96. So 96% of the variance can be explained with these four dimensions. Then it's a valid idea to say we get rid of the other 6 dimensions in the new space, yeah, of the principal component analysis, and only look for the first 4. Yeah, so we start with the dimension that has the highest loading, and we add further dimensions, often until we exceed a certain threshold that tells us it's not necessary to look at further dimensions because their influence will be really small. Yeah? The projection error is minimized for any selection of n. Yeah? That is a property of the principal component analysis. Let's look at some examples. Here we have data from Wikipedia, officially registered data about a number of countries. Here is the life expectancy averaged over males and females. The poverty index that tells you a bit how unequal a society is. The average household income, yeah, that could be quite different between 67,000 US dollars per year in Canada, 10,000 in China, and less than 1,000 in India or in Russia. Yeah? So these are examples of the data. Yeah? In total, it's 50 variables. So what you see here are only 6 of them. That's abbreviated. Yeah? Here you see the result of a principal component analysis. And we look here at the 2 major components, Z1 and Z2. And Canada, for example, has these values. Singapore here has for Z1 lower value. The Z2 value is instead a bit higher. Yeah? So Z1 and Z2 are linear combinations, weighted combinations of these original variables. The problem is, maybe you have noticed it already, it's not clear what Z1 and Z2 are meaning. Yeah? What is their semantics? Here they are visually shown, all the different countries arranged here in this scatter plot composed of the 2 dimensions that correspond to the first and second principal component from principal component analysis. Here we see large countries. The US is one example. There are others like Turkey or so. These are here and have high values for Z1. Singapore has a similar way in the Z2 dimension like the US, but it has a considerably lower value for Z1. Basically, Z1 is high for larger countries and small for smaller countries. And Z2, what does this mean? Z2 basically is a measure for the per person productivity and the well-being of persons. Yeah, so the status of the healthcare system. And there, Singapore and the US are approximately at the same level. Yeah, so that could be an explanation of this principal component analysis result. Yeah, let me briefly explain the principal component analysis. First, we have to normalize the data. Yeah, we have data in different ranges, pressure, temperature, and so on. For example, we need to normalize this. Then we compute the covariance matrix. The covariance matrix means that we take all our measurements, write them in a matrix, all our data sets, and we compute the transposed matrix, and that is our new matrix, namely the covariance matrix. And that is normalized by dividing all these entries with the reciprocal of the number of items in the data set. Yeah? So that's the covariance matrix. The covariance matrix is a symmetric matrix. That means the elements on both sides of the diagonal are the same. And it's also a matrix that has the property of being positively definite. Yeah? Positive definite matrix. Based on these two properties, one can reliably say for the covariance matrix there are n eigenvalues and eigenvectors also, and the eigenvalues are real valued numbers, not complex numbers. Otherwise, there could be complex numbers. Yeah? But here we can rely on the fact that they are real values. An eigenvalue of a matrix is something, if I multiply the matrix with a vector, then I get a vector as a result. And if I compare this vector with a vector that I have multiplied with an eigenvalue, then I get the same result. And if this is the case, then this factor, lambda it's often called, is an eigenvalue for this matrix, and the vector v that we have used for this computation is the corresponding eigenvalue. So a matrix like the covariance matrix can be decomposed into a matrix, an eigenvalue, and a transposed matrix. Yeah? And this lambda here is the diagonal matrix, which means all the elements in that matrix are 0 except the diagonal elements. Yeah? So U is what we want to have, is an orthogonal matrix. That means the vectors there are independent from each other. And this matrix contains the eigenvector and also the eigenvalues. For dimension reduction, we choose a certain error rate and accept an error that we make that is in this dimension, in this range. It could be 1%, 5%, or 10%, for example. Yeah. So maybe we are sufficient if we are fine if we can explain 90% of the variance in the data. For visualization purposes, this K is often chosen such that we only have 2 or 3 dimensions, because that is everything that we can show at least in one scatter plot. Yeah? So here we see examples of visualizations, principal component number 1, principal component number 2. Also the variance is mentioned here, 21% and 60%. So here the first principal components have less than half of the variance of the data. Yeah, but that is what you see here, embedded again in these concentration ellipses. And here we have a similar thing in 3 dimensions. Yeah, let me explain this also with an example. We have data from sportsmen in Decathlon, in German Zehnkampf. Yeah? So they have to they have disciplines where they have to throw something, yeah. They have disciplines where they have to jump high and far, and they have disciplines where they run 100 meters, 400 meters, 1500 meters, yeah. So for every sportsman we have 10 results, and we are interested in the fact whether we can characterize the performance of a sportsman in decathlon with fewer values instead of the 10 measured values. And if we use these 10 measured values and apply a principal component analysis, then we can reduce this to 2 dimensions, and we see here the names of different sportsmen. Yeah? And we see these 3 persons, these are the ones that have won this competition. Yeah? Scheberle, that's a Czech person, was the winner. Clay and Karpov were second and third. And if we would add the places of the other persons here as well, it would become obvious that basically this dimension, the x dimension, separates the best sportsmen from average sportsmen in this competition. They are all very good, of course, and those with the lowest results. Yeah? So that is one dimension here. The second dimension basically discriminates sportsmen that are fast in running and good in jumping from those athletes that typically are a bit bigger and have a higher weight, and these are better in disciplines like shot put and discus throwing. Yeah, that's the second dimension. Here we see for this result the influence of the original dimensions. Yeah, 1500 meter run, 400 meter run, hurdle run, and so on. You see that some of these lines are smaller and others are higher, so they do not have the same influence on the results, at least not in this specific example. Yeah, yeah. What we can also do to assess the results of a principal component analysis, we could look at these scree plots that tell us the variance of the first principal component, the second, and so on, in addition to the cumulative influence of the first n dimensions. Yeah, that is what we see here or in this diagram form here. What we do not easily see with these scree plots is what is the influence of the original variables on the principal components. Yeah? So for example, how this principal component number 1 is related to the original data that we have measured. That would be, of course, an interesting information for an analyst. Yeah? Just a second example where we see this loading plot with arrows that have a certain direction and a certain length, and the length here indicates the influence of, for example, mean grain size in this maritime geology example that has, based on this large vector, a larger influence on the result, like distance from tsunami source or protection factor. Yeah, that was a little bit of a simple example. Here we have a more complex example from mass spectroscopy. Many measurements have been derived, elements have been classified with a clustering algorithm, for example, and now we see the result of applying principal component analysis. Here is the PC1 loading, and here is the PC2 loading. Yeah, so that would be a result for a more complex situation. I mentioned already that outlier sensitivity is a problem with principal component analysis and cluster preservation as well. Yeah. So therefore, variance is often not an ideal interestingness measures. The classic principal component analysis is sensitive to outliers and also, yeah, it's not necessary does it perceive, does it preserve clusters. There is a variant called robust PCA, where among others the data is normalized with respect to the variance of the data. That is not so sensitive to outliers and clusters. Yeah. So here is an example for another variant called supervised PCA, where the user has a bit more influence and you see that this result is better than this one, and it was achieved because it was a kind of supervised principal component analysis where the expert had a certain influence to visually separate the elements that we have. Yeah, this is an example of two screenshots from a talk from Luis van der Maten. He developed this T-SNE technique that I will explain in the next video lecture. And he applied principal component analysis here to the digit dataset. The digit dataset contains of handwritten numbers, so people wrote 1 and 2 and 3, yeah, and they do this slightly differently. And the question is, if we analyze them pixel-wise, which of these numbers really have a high similarity. So ideally, all the numbers written as 3 should be similar and strongly different from a number like 5 or 8. Yeah, but that is not necessarily the case. Yeah, in our example, it shows that with color coding, the digits are separated quite well. Yeah, principal component analysis is a linear projection method. That's essential. It assumes normally distributed data, and with this, clusters are typically not preserved. Yeah, the dimensions need to be centralized. That means everything is scaled around 0, and moreover, it is normalized, which means that it is divided by the range of the standard deviation of the data. That is called autoscaling, yeah? Centralizing combined with normalization. The drawback of this autoscaling is that noisy measurements are scaled up. Yeah? We have slight differences in the data that are not very meaningful, that are just the result of a noisy measurement process. But now, when we incorporate this technique, we do not get the right values. We increase the noise, and as the second drawback, it may happen that large peaks in the data that are really meaningful are reduced to a strong extent. So autoscaling is necessary for PCA, but it involves some severe drawbacks. Strongly correlating results dimensions are also not ideal for principal component analysis. So I've seen many papers that recommend to remove upfront the correlating dimensions. Yeah, that could be achieved with feature selection. The problem with principal component analysis is the interpretation of these new dimensions. I showed this in two examples. We looked at the decathlon example, where one dimension represented the overall goodness of the sportsman, whereas the second discriminated a bit between specialists in running and jumping compared to those in throwing something. And we have seen these other examples of the countries and the elements that were available, the data that was available, that characterized the well-being of the country. Yeah, but that is really a challenging process where the user needs to be involved, and he also needs some help in order to make sense of the resulting visualizations. Yeah. An alternative use of a principal component analysis would be that we determine a set of dimensions from the original data that explains most of the data, and we really remove other dimensions. Yeah? Principal component analysis does not remove dimensions. With a certain weighting factor, all the dimensions will be included in the new dimensions. Yeah? So here we could remove them, and we then apply principal component analysis, look at the loadings, and remove dimensions from the new dimensions that we have now computed, where the loadings are quite small, until we have the desired number of dimensions. There was one, I think, quite substantial development called interactive principal component analysis, where principal component analysis was embedded in an interactive system. weights for the dimensions could be adjusted. For example, points could be manipulated, and the results were shown in 4 different coordinated views. I think the video that was produced in order to enhance this publication is quite useful, and I think we look for the first 2 minutes together at this video. It's a 5-minute video. Let's look at this.
We demonstrate our system for interactive visual analysis using principal component analysis. The interface of our system consists of 4 coordinated views. Interactions with one view is immediately reflected in all of the others. The projection view shows data points projected onto 2 principal components. The data view displays all data points using parallel coordinates visualization. The eigenvector view displays the calculated eigenvectors and eigenvalues in vertically projected parallel coordinates. The distances between eigenvectors vary based on their eigenvalues. Lastly, the correlation view shows Pearson correlated coefficients and relationships between all possible pairs of variables. Our system provides 2 different sets of interactions: interaction with views and interactions with PCA. Interaction with views include zooming, panning, as well as selection of single items and range selections. These operations are available in all views, and the selected data items are coordinated in the view through the use of colors. Interactions with PCA are operations that allow the user to manipulate the values of data items. The user can either modify single data items or an entire dimension. In these interactions, trails can be enabled for seeing the recent changes. Furthermore, data items can be temporarily removed from the PCA calculations. This can be done either as a single data item or a group of data items. Now we demonstrate how the system can be used to perform analysis using PCA. In this scenario, the user is trying...
That's enough for the moment. So we close this. I wanted to show this to you because it really shows a connection between the data after dimension reduction with the original higher dimensional data. Yeah, that was one essential property of the system. However, one must admit the data had not many dimensions. That was the iris dataset, as you may have recognized, that only has 4 dimensions. Yeah, so that technique would not work so convincingly if we have, let's say, 12 or 15 dimensions. But I think some nice ideas are based on this paper. So as the second linear technique that I want to explain, I briefly describe factor analysis, not in the extent that I have done it with the principal component analysis. So I would not ask you in an exam, explain to me in detail how factor analysis works, but just to give you an intuition also about this second frequently used linear dimension reduction technique. It provides no ranking of the dimensions as we saw it in the principal component analysis. Yeah? So that is one of the major differences. The goal here is in factor analysis that analysts want to analyze and identify common causes of measured data, latent factors. Yeah? So the variance of the data is explained by a smaller number of factors and clusters consisting of different variables. The origin of this was from psychology and in particular from intelligence tests. Yeah? Psychologists wanted to characterize verbal intelligence, mathematical intelligence. There are other variants of intelligence. And for each of them, many test results are available. And the question is, how these test results could be summarized to certain meaningful aspects of intelligence. Yeah? Factor analysis is not only used in these examples, it's also used for language recognition. So the data is first normalized and centralized. That is what you have seen with PCA as well. That is autoscaling. And then pairwise correlations of the items are evaluated. And that is done with respect to the scalar product of the items. Yeah? That yields a certain angle. And that is the dot product of the two vectors. Yeah? That is a technique that we have described once, that's also used for clustering document collections. Yeah? And based on the analysis of this angle alpha, subspaces of highly correlating variables are determined. And the observed variables are modeled as linear combinations of the potential factors plus an additional error term. Yeah? So here would be an example for a result. In a questionnaire, people were asked how talkative they are on a certain scale, how shy they are, how sociable they are, and how much fun they had. And it turned out that these four variables can be summarized in a measure for whether this person is more extroverted or introverted. Yeah? And in a similar way, here are 3-4 attributes that can be summarized to one concept that was identified as a latent factor, basically responsible for these four variables, so that we have one attribute that summarizes this quite well. Yeah, then let me describe projection pursuit as a further linear dimension reduction algorithm technique from Friedman and Tukey already from the 1970s, computationally very efficient, and you can imagine that this was highly important in the 1970s when computer power was a bit lower, to say it politely, than it is today. They compute an index for every dimension that measures how well this dimension separates the data. Yeah? So if the entropy for a dimension would be low, this index also would be low. The resulting projections, primarily 2D projections, reveal clusters very well. But projection pursuit could also be realized in the way that it was applied to individual clusters. Yeah? That means not all data is projected in the same way, but 3 or 4 clusters, for example, are projected in a different and adapted way. And it turns out, based on the evaluation that the authors did, that the combination of clustering and projection is quite effective for exploratory data analysis. I really like the approach of the authors. Yeah? In the 1970s, that was far from typical that scientists work like this. They really observed researchers how they explore multivariate data. They wanted to understand the process of the domain scientists. For example, they saw that the researchers often rotated three-dimensional views of the data. And certain projections were carefully inspected, namely projections where the data is spread very well, yeah? Where the whole space is used to a large extent, and projections were looked at quite carefully for a longer time, where regions with a high local density could be observed and are recognizable. Yeah? So the projection index that they assign to every dimension is a combined measure of spread, yeah, the first observation, and local density. Yeah? And spread is basically computed or in a similar way like the standard deviation. And local density is the average distance of point pairs within a cutoff radius. That could remember you to the discussion that we had on the kernel density estimation for some advanced variants of scatter plots. Yeah? And as a preprocessing for the projection pursuit, all dimensions have to be transformed in such a way that their variance is similar. The algorithm starts with an initial set of directions for example, principal components or original directions, and then iteratively the directions are optimized with respect to this projection index until we achieve convergence. That means in one iteration the improvement is very small. With this we compute a local optimum, so we cannot be sure that we have a global optimum. Therefore, it is a good idea to use different starting points and thus compute different projections. For the examples that the authors tried, 20 to 30 iterations were typically sufficient. And their technique was rather robust against the cutoff radius that was used for determining the local density. Yeah, here we see examples, again the iris dataset with two clusters, one that has a rather low density compared to the other one, but slightly more members. And what you see here is an application of projection post-suite to this cluster, so to a subset of the data. Yeah, some properties of projection post-suite: it ignores noisy and information poor dimensions quite well. Yeah. The interestingness measure that is incorporated here in the projection post-suite can be adapted. Yeah, there are different variants. The Fisher-Tukey index is one that was suggested. Most of the interestingness measures that were used consider a dimension as interesting, or projections as interesting, where the resulting distribution of the data deviates from a Gaussian distribution, from a normal distribution. Yeah? The more unnormal the distribution is, the more it is considered as interesting here. Yeah? Often a cluster is identified and explored in a separate view, removed from the data, and projection post-suite is applied to the remaining data. Yeah? So these are some essential properties of projection post-suite. Yeah, let me summarize this first video lecture on dimension reduction. I introduced the topic as a whole. Why do we need dimension reduction? I contrasted feature selection with dimension reduction, where feature selection really removes dimensions of the data, whereas the linear dimension reduction techniques provide a new coordinate system where all the original dimensions contribute. We also briefly looked at a projection error, for example, in a principal component variant analysis, that is the explained variance, or it is 1 minus the explained variance. Yeah? Often the linear projection techniques are not so suitable if we really have high dimensional data, and also if the distributions in the data strongly deviates from being normal. So I make a small advertisement at this point. In the next semester there will be a seminar. Yeah? Depending on how many people there are, I make it alone or with Gabriel Mistelbauer. The topic of this seminar is visual analytics in healthcare. Yeah? So it's something as a more specialized variant of visual analytics, namely emphasizing medical applications. Yeah? Often this is combined also with spatial data. So here, for example, you see a map and overlaid some health-related data, like how often a disease occurs, corona or whatever. And here you see epidemic modeling, decision paths. How can visual analytics contribute to decisions in case of a pandemic that have to be taken? What is the likely influence of school closures or other measures? That also is a nice example for visual analytics. We will also look in patient data. Yeah? So here, for example, many data for one patient is available, summarized according to different groups of symptoms. Ultrasound images are incorporated. So how can we come up with good decision support for clinical practice? Yeah? Other aspects of visual analytics in healthcare are clinical health information. where the data is typically summarized in electronic health records, but also public health information, where state governments, like even the World Health Organization, collect public health data and want to support health policy. The major difference here is in clinical situations, we have persons that are ill and need urgent treatment, whereas public health tries to a large extent prevent diseases. Yeah, you have experienced all these measures against corona that basically serve the purpose of preventing that persons get ill, not to repair when they are already ill. Yeah, and public health is particularly interesting because we have really large amounts of data there. But even the data for an individual patient are quite high dimensional. They are also time dependent data. And yeah, they serve to understand how patients react to previous treatments on a scale of weeks or months. Yeah. Cohort study data, there we don't have patients but healthy participants, and we collect many answers to questionnaires, but also laboratory values, and we follow up these participants over longer periods. So we are involved in one study that started in 1997, and every 5 years the participants are asked again to participate in this study, so that one really can better understand which risk factors, for example, have a certain influence on diseases. Yeah, so that was my advertisement for the seminar in the winter semester, Visual Analytics.